So if you correctly follow the step mentioned in the previous section, you'll be able to install Vivado 2020.2 along with Xilinx Vitis 2020.2, right? In this section, we'll try to understand the fundamentals of both Vivado as well as Vitis, which is required for an embedded system design, right? So let us just check whether configuration of an tool chain is successful, right? So here what we're going to do is we will just be writing one simple application code on an Vitis and try to perform an execution of that code on an FPGA board, right? So for this demonstration, you require to connect FPGA board to the PC, okay, so that at the last step when we download a application on an FPGA, we'll able to verify whether the code is working as expected, right? So if you do not have an FPGA board, it doesn't affect much because only the last step where we verify the code on an hardware is something that you'll be missing, right? So you could actually follow an entire process and try to get most of the codes, right? So let us just go ahead and double click on an Vivado 2020.2, right? So this is how we start our application development, right? So once you double click on an Vivado icon that you have on a desktop, you'll be able to get this GUI, right? So we start with create project. Once you click on create project, this will automatically start a new project wizard, right? So we click next and then you get an option where you could specify the project name as well as directory. Okay, so for an entire course you could keep one separate directory where you have all our project located in a single directory, right? So here we will be sticking to the default project name as well as the directory that has been chosen by Vivado, right? Click next. Remember the directory is project_30, right? Click next. Here we will be choosing RTL project. Click next. Then we get an window where we could specify the source. But if you consider an embedded system design, so we build our system with a graphics based methodology. Okay, so we will be utilizing Vivado IP integrator. Okay, and there we will be building our hardware design, right? And after we complete our hardware design, from that block design itself we'll be getting the HDL source, right? So we do not need to explicitly add any source, okay, when we consider an embedded system design. So we'll just be choosing that the target language is Verilog and the simulator language is mixed. Like click next. We do not need to add constraint at this time. Click next. And then the board that we're gonna use for this specific demonstration is the Basis 3 board, right? In fact, you could use any board that support Microblaze, right? So we go ahead and we select Basis 3, right? Click next and then click finish. So this will automatically create the multiple directory which are required for an embedded system design. Okay, in the project_30 we will be understanding what is the content that we have in this directory as we progress further, right? So our Vivado project is ready. We start with create block design, right? So in an IP integrator you see an option to create a block design. Okay, so just click on it and click OK. So here we have a canvas where we could create our hardware design, right? So first we start with adding a Microblaze IP. So click on this plus button. So you have two options to add an IP. Either you could click on this plus button or you could click on this plus button, right? So if you just click on this plus button, you get the series of IP for which you have a license, okay? Or in fact the inbuilt IP that you get with an Vivado, right? You just need to look for a Microblaze, okay, and then you just need to click enter. So that will automatically add a Microblaze onto a canvas. And the first thing that we do whenever we add an IP is to perform a block automation, right? So this will apply a board preset, okay, that basically mean you get the clock source, a reset circuitry and the local memory for a Microblaze, right? So we'll be clicking on run block automation. And the only thing that we need to specify over here is the local memory requirement that we have, right? So we'll just be choosing the maximum memory requirement that is allowed, that is 128 KB, and we'll click OK, right? So once this is done, this will automatically perform a board preset for us, right? That will add some of the ports to our Microblaze IP, which could be used to interface the further component with the Microblaze, right? So you could clearly see we have a process system reset been added. Okay, the clocking wizard IP is added and we also have a local memory, right? In fact, you could see we also have an MXCDP port, okay, that could be used to connect the slave XI peripheral with a microblaze, right? So with this thing done, we will start specifying the clock source, right? So on a basis 3 board, we have a single-ended clock. Okay, so to specify that, we just need to go to a clocking wizard. Okay, and usually the clock source that we have in an board files, okay, are referred to as a sys clock, right? So you could see we have a clock one, which is the source for our clock, and it has been selected as a differential by default, right? To correctly specify the clock that is available on a board, we just need to go to clock in one, and instead of a custom, you just refer sys clock, right? So this is how we refer the clock in a board file, right? So we have a sys clock over here. The other thing that you need to make sure is the reset type is correctly selected for the specific board, right? So if you incorrectly specify the reset, so as you program your FPGA, you'll be getting an error that SDK or a Vitis is unable to reset your Microblaze, right? So if you get that error in a Vitis, so that basically mean you have selected an incorrect reset type, right? So for a basis 3 board, the reset type is active high, right? So we will be going to an output clock tab, and here we have chosen an active high type, right? So lock pin is not necessary. We could just uncheck it, right? So we have a clock in where we will be connected a system clock. Clock out is giving to all the IPs a clock, and then we have a reset, right? So with this, we'll just be clicking OK. And now once we correctly specify the clock source as well as polarity and the reset type, we are ready to perform connection automation. So just click on connection automation, select all the ports which have been mentioned over here and click OK, right? So with this, now you could understand we have reset been connected to the respective hardware pins. The clock is also connected to the clock source that is available on an board, right? Now we go ahead, and in this specific demonstration, what we're going to do is we will be sending some random string onto the UART, and we'll be analyzing whether we're able to receive the data onto the console, right? So we go ahead and we add UART light IP to our canvas, right? So once you add an UART light IP to a canvas, we automatically get an option for a connection automation because our Microblaze already have an MXCDP port to which we could connect the slave interface of an IP, right? So we'll just be going ahead and performing a connection automation. So once that is done, you could now see we have Microblaze and MXCDP port is connected to an AXI interconnect and finally to UART light, right? So AXI interconnect handles the transaction between the Microblaze and the UART light, right? So even though we have a single MXCDP port to a Microblaze, but AXI interconnect allows multiple IPs to communicate or interface with a Microblaze, right? With this, we can proceed to perform validation of design, right? So validation of design verifies whether all the mandatory connections are connected to their respective pin, right? So if validation is successful, we are ready to proceed for generation of an HDL code, right? So validation is successful over here. Now we haven't configured our UART light IP. So just to observe the rate at which it will be operating, we can just double click on an UART light IP. We go to an IP configuration, and you could see the baud rate at which it is operating is 9600. We won't be configuring it. We'll be keeping the same baud rate, right? And our validation is also successful. Now, the next step is to calculate the number of ports that we have in our design, right? So you could clearly see we have one port, which is reset, second port that is sys clock, and the third port is USB UART, right? Now we go to a board tab which reflect all the peripherals that Vivado recognize from a board file, right? And once you connect the port to the respective hardware pin, you'll able to see an yellow check mark over here, right? And all the peripherals which are not connected or used in a design will be simply having an hollow circle over here, right? So you could see sys clock. Okay, so sys clock is our input clock source that is available onto an FPGA board that has been connected to this sys clock pin, right? And reset signal and USB UART is also been connected, right? So you just need to make sure that the number of ports that you have designed have the number of check marks in this board tab, right? So here we have a 3 check marks and we also have a 3 port. So for example, if your design consists of more ports than the check mark that you see over here, then you need to follow a different process. That is, you need to then perform a synthesis first. Okay, then you need to specify the ports or the pins of an FPGA where you will be connecting the remaining port, and then only you could proceed for generation of a bit stream. But here, since all the ports have been already mapped to their respective pin, okay, we could directly proceed for generation of a bit stream without performing an intermediate synthesis, right? So we go ahead to a source step. Now in the design source, you could see the design one, right? So this is our block design, and to generate an HDL code out of it, because ultimately the flow navigator, the different option that you see over here, work on an HDL, right? And here you have BD, that is block design, right? So we need to convert this block design to an HDL before we proceed for the design flow. Okay, so we select our block design, and then you have an option to create an HDL wrapper, right? So you just need to right click on a block design. So just right click on a block design and select create HDL wrapper, right? So this will automatically generate the VHDL or a Verilog code depending on the language that you have chosen, okay, out of this block design, right? So our HDL code is ready, right? And this has already been set as top model, right? So once this is done, we will be going ahead and generate bitstream, right? So you'll be following this procedure only when the number of ports that you have in your design matches to the number of check marks that you see in a board tab, right? So if the check marks are not matching, you need to perform a synthesis. You need to specify the constraint, okay, that is connection between the ports that you have in your block design to the FPGA pin, and then only you need to proceed for generation of a bitstream. Okay, now this will take a bit of time to generate the bitstream, and once bitstream generation is successful, we'll proceed further.